Hello and welcome to Chapter 8, Section 2. We are doing number 31. And in this problem we are given that the London Ferris wheel has a diameter of 450 feet and makes one complete revolution in 30 minutes. We are then asked to find the rate in degrees per minute that the London Ferris wheel is rotating. Let's start with that. So I have a little bad drawing here of a circle with a diameter of 450 feet, and I've stated that one revolution takes 30 minutes. So we want to know the rate in degrees per minute that the London Ferris wheel rotates. So we have this, revolutions per 30 minutes. We know that one revolution, the Ferris wheel is circular in shape, so one revolution is equal to 360 degrees. So 360 degrees divided by 30 minutes. It's simple math. 360 divided by 30 is equal to 12. So it takes 12 degrees per minute. And so then question B says, let t, the time in minutes, be 0 when you are in the 6 o'clock position. Write theta measured from the 3 o'clock position as a function of t. So sketch this here. So at the 6 o'clock position, t equals 0. Throw a little t over here, t equals 0. And we want to find theta as a function of time when measured from the 3 o'clock position. So to do this, first of all, we need to find the difference in angle between 12 o'clock and 3 o'clock. Well, we know that on a clock, the line formed with the 3 and the 9 and the line formed with the 12 and the 6, these two lines are perpendicular with each other, so we know that this is a right angle and equal to 90 degrees. We also know that from A, that this goes in 12 degrees a minute. So we need to figure out how many minutes does it take for this angle to reach 90 degrees, to get from 6 o'clock to 3 o'clock. And we're going to go ahead and assume that the Ferris wheel is rotating in a counterclockwise direction. So 12 degrees per minute, so 90 divided by 12 is equal to, I believe it's 7.5, but let me check. Just to make sure. Yep, 7.5. Never hurts to check yourself. So that's how long it takes for this angle to reach 90 degrees. So, and then we also want to keep in mind that any value we plug in here for t, if it's 0, then we're going to want this angle, since we want the Ferris wheel to be rotating counterclockwise. If we're going to measure it from this axis, if t equals 0, then theta better equal 90 degrees. If t equals 7.5, then theta better equal 0. If if t equals 15, then theta better equal 90 degrees, right? So let's make this equal. So how would we make this equal to 0? Well, we'd make theta equal to 0 by saying 12t minus the distance from the 6 o'clock position, from the 3 o'clock to the 6 o'clock. So that's 90 degrees, minus 90 degrees. So to make this equal to 0, this would be 7.5. And so really to get the distance from the 3 o'clock, it's just 12t minus 90 degrees. Because if we go, so let's say 12t were equal to 4 minutes. So we'd multiply 12 times 4, right? We'd multiply 12 times 4, and we'd find that t equals 4, it would make an angle here of 48 degrees. But that's relative from the 6 o'clock axes. We want it from the 3 o'clock. And so we'd subtract 48 from 90. And we'd find that from the 3 o'clock position, it would equal 42 degrees. So this will work for any minute. It'll give you first, this is equal to the angle relative from the 6 o'clock, and then subtract 90 in order to get the angle from the 3 o'clock. It probably took a little bit more explanation than was needed, but that gave us our equation, 12t minus 90 degrees. And this will give us the angle theta from any position relative to the 3 o'clock position. And I'm going to move C up just a little bit so we can see it better. Aha! And move C so we can see. And now we're asked to find a formula for the Ferris wheel function h equals f of t, giving your height in feet above the ground. So normally we work in radians when doing these circles, but this problem had us convert the revolutions for 30 minutes to the revolutions in degrees per minute. So we're going to stick with the idea of degrees. So we actually already have our b factor. Notice that this is a period, and that we divided our period by the degree equivalent of 2 pi. 360 equals 2 pi. So, or 2 pi radians. So we have here, we divided this, our 2 pi, by our period, and 12 is our b. Let's go ahead and start writing things down, because writing things down is a good thing to do, and that's how you solve for your equations. Equals, okay, so we have b is equal to 12 degrees. We need to know what sort of vertical stretch we're going to do. Well, we're not given anything to shift by. First of all, there's no little distance between here and the ground that we're aware of. I guess we're just going to assume that this thing is touching the ground, so it's highly unlikely, but you know what? What the heck? We need to find how much, we need to find, first of all, the amplitude. We know that it's going to be oscillating around, divide 450 by 2, because this height, this distance is going to be the same as its vertical height. So divide 450 by 2, and you'll find that that equals 225. So it's going to be vertically stretched by 225. And then we need to decide whether or not we're going to use a sine or a cosine function, right? Let me fix this 5. I'm feeling a little bit OCD today. Well, if we start from the 6 o'clock position, this would be a sine function, or not a sine, this would be a cosine function. Or it would be vertically flipped about the x-axis. It would have been reflected across the x-axis. But we already have a nice little equation here, or formula here, if we were to do a sine function. Because I can show you this really quickly, just, in case you don't understand why. Like, pretend this is an x-axis. I'm going to put a hat on here because I'm in physics and I'm used to that. Pretend we have this little line here, and pretend this is the x-axis on a normal sine or cosine function. So we know that these tick marks, let's pretend these are important places. We know that this would be pi over 2, and this would be pi, and this would be 3 pi over 2, and this would be 2 pi. Well, remember what the degree equivalents to these are. Pi over 2, 90, pi is 180 because pi is half a circle, 270 degrees for 3 pi over 2, and we just discussed this is 360. And these are all degrees. Here, these are all degrees, and these are all radians. So, what do you have to do to shift a sine function to get a cosine function? Well, you're going to have to shift it left or right, but the easiest way to shift it is to shift it pi over 2 units to the left. And that's the easiest way. That way, your maximum I'm sorry. Your maximum will line up with the cosine maximums, and you will be set and good to go that way. So, but notice, the funny thing is pi over 2 is 90. We've already done that with this equation, right? And t is our input. And so we actually have everything we need to make this sine function equal the cosine we would use. And so let's just go ahead and stick with this. Sine 12t minus 90, this is degrees. And then we have to know how much we need to shift it for us to get to the midline, or to the middle of the Ferris wheel. And the amplitude and the midline are, again, as they have sort of consistently been throughout this homework, they're again the same values, so plus 225. So let's take a look and see how this compares with the homework. And our homework says f of t and then disappears and goes a line below, and I'll show you what I'm talking about. So it says f of t equals 225 plus 225 sine 12t minus 90 degrees. Cool. Well then, how about that? So this is our formula that models height, and this is that for theta. Cool. And so then there is a letter D. I'm not going to do letter D for you because, I can show you how, there's really no point in me doing that for you. But we can take a look. You need to find the amplitude, you need to find the midline, and you do need to find the period. And we've discussed every one of these already, right? So you should have no trouble going through and finding those on your own at this point. So I am just going to leave that up to you. Alright, I will see you in the next video.